One thing that should be familiar to you from previous chapters is using a leaving group, seeing a leaving group, seeing that as a gateway to the world that allows you to do substitution and elimination, and using that to create one pi bond by doing elimination. So remember, if you have a leaving group, the carbon that the leaving group is on, that is called the alpha carbon, and then each carbon next to that is called a beta carbon. Now those beta carbons could have hydrogens that can be stolen or ripped off by a base. Notice in this particular molecule there are no beta hydrogens to the left. On that beta carbon to the left, that carbon is already bonded to 1, 2, 3, 4 carbons. So there are no hydrogens there, and so a base could not steal any hydrogens from that direction. So you wouldn't be able to do an elimination in that direction. On the other hand, there are hydrogens here. There's 3 of them. Just for clarity, so that it doesn't look cluttered, I'm going to only draw 1, but there are 3. This base can steal one of those. The electrons can snap toward the leaving group and kick the leaving group off. So this would be an E2 mechanism. We have a proton transfer on the top and loss of a leaving group on the bottom. And when you're done, you'll notice that you have the same molecule, or at least the same carbon chain. It's just you don't have the leaving group anymore, and instead you've formed one pi bond. You've formed a pi bond. Okay, so that's something that we saw previously for alkenes. Now, what we're going to see now is a reaction for alkynes, but the same idea. What if, instead of just one leaving group, we had 2? If we had 2 leaving groups, then we can do this reaction twice. Because you still have the alpha carbon, you still have, in this case, only one beta carbon that has beta hydrogens on it. Remember, this one doesn't have any beta hydrogens, so the base can't interact with that to cause an elimination reaction. So we'd have 2 hydrogens that can be stolen, 2 bromine leaving groups, and so we can do 2 eliminations and create 2 pi bonds. In other words, instead of creating an alkene, we could create an alkyne. Now to do this, you'll want to use something, you'll want to bring out the bigger guns. You'll want to use a little bit of a stronger base than sodium hydroxide. So what base would be a good base to use for this? It's going to be a common base in this chapter. If you think of ammonia, ammonia is the nitrogen version of water. It's NH3. When you were first introduced to that in General Chemistry 2, and we talked about it earlier in Chapter 3 of this course, we represented that as the poster child for a Bronsted-Lowry base, because this lone pair that it has is able to accept H pluses. So that's a base already. But what if you take the conjugate base of that base? What if you take an H plus off of that molecule? So it's an H2 with a minus sign, because you took an H plus off, and now it has 2 lone pairs instead of 1. That is a very strong base. And it's often stabilized, that negative charge is often stabilized so it doesn't explode in a beaker or in a storage container. It's often stabilized with a sodium ion, Na+. So together, because these 2 charges cancel each other out when they're combined, this will be written NaNH2. But really, this is this base here, once you put this into solution. And sometimes this, because you can't put this in water, this will just steal the hydrogens from water, and you'll just end up getting, water will turn into a bunch of hydroxides after the hydrogens get stolen. So you can't put this in water, so instead the solvent that they're going to put this in is NH3. So sometimes you might see this as /NH3. That just means that it's in an ammonia solvent. NH3 is ammonia. So if you have this base, and notice you're going to need more than one equivalent of it, you're going to need excess of it. When you put this into solution, the sodium goes its own way. It's a big atom, spreads and dilutes that charge out, and is really stable. The nitrogen, on the other hand, is not. And so it's a really strong base. The first equivalent steals one of these hydrogens. The electrons go toward the leaving group and kick one of the leaving groups off. So after that first step, what you are left with is the carbon chain mostly stays the same. None of the carbons disappear or appear, so in that sense it's the same. We only have one leaving group now. This bromine has left, so we only have one bromine left. One of the hydrogens is left, and so we have a pi bond here that we made from its electrons. Now, I drew 2 hydrogens here. There are actually 3, but only 2 are going to participate in the reaction. So I'm just drawing the minimum number so that it looks less cluttered. So if we have excess of this base, then another equivalent can come in. Another equivalent can come in, and it can steal a second hydrogen and do another elimination reaction. Those electrons go toward the leaving group and kick the leaving group off. So what we have after that and notice I'm going to draw this in a zigzag first, but then I'm going to redraw it because triple bonds are linear. So notice we get that extra pi bond there. But when I redraw that molecule to represent its actual shape, it looks like this. So notice we have 1, 2, 3, 4, 1, 2, 3, 4. Okay, and so that would be the last product that we'd have here. We'd form that alkyne by doing 2 eliminations. The thing is, this is a very strong base, and as we'll see in future exercises, the hydrogen at the end of this is very acidic. So if you have excess sodium amide, another NH2 can come in, steal the hydrogen here, and that electron goes back on the carbon there. So that would leave us with a relatively unstable molecule. And so what you'll do after after you treat this with excess base, excess sodium amide, NaNH2, is you just shake it up with some water, and you do a proton transfer from water. This steals one of the hydrogens from water, and the electrons snap onto the oxygen, so that overall you have the hydrogen back. Now I'm drawing this mechanism a little bit quickly, and I apologize for this crunched space here. But I just want to give you a sense for how this reaction really fits into what you already know. It is making alkynes using a excess strong base and water if you have 2 leaving groups. So really, we've just drawn the mechanism for this exact reaction. This is the exact molecule we were just using. This excess strong base steals the beta hydrogens, 2 of them, kicks the leaving groups off twice, and creates a triple bond. And make sure you draw that linear, just like we did above. So it steals the base once, steals it twice, creates the 2 pi bonds in the alkyne. In addition to that, unfortunately, the excess base would steal the hydrogen off of that carbon at the very, very end of the chain, the carbon, that sp hybridized carbon that has the hydrogen there. And so after you're finished doing the excess base, you just shake this up with water to put the hydrogen back on through proton transfer. And so that's the product you'd get here. You'd look for the carbon that has 2 beta hydrogens, and you would draw the triple bonds in that direction. You'd erase the leaving groups, and that gives you your molecule. Let's try it with another one. This one is also a dihalide, right? This has 2 halogens. This has 2 halogens, so those are dihalides. These are slightly different. These 2 halogens are on 1 carbon, so they're twins. They're called geminal. This is a geminal dihalide. The word Gemini just comes from the Greek word for twin, And these halogens are not on the same carbon, so they're not twins. Instead, they're neighbors. And so the Latin word for neighbor is in this case, just if we anglicize it a little bit, it's vicinal. So this is a vicinal dihalide. Now you can do elimination reactions to create alkynes, either with geminal or vicinal dihalides. With vicinal dihalides, you're going to create the triple bond in between the two leaving groups. So if you're just thinking about it from synthesis, not thinking about the mechanism, but just thinking about drawing the products, you can redraw the zigzags if you want. You just have to make it linear when you're done. And in between the two carbons that have the leaving groups on it, that's where you put the pi bonds that you get when the base steals the beta hydrogens and kicks the leaving groups off. So you just want to make sure you redraw that so that it's linear. And that's it, that's your product. You'll notice that they have the same number of carbons. So 1, 2, 3, 4, and here I'm just numbering it to keep track of stuff. I'm not numbering it in the way that I would to name it. But you can see you have the two methyl groups on carbon 3, and you have the, in between 1 and 2, where you had the leaving groups, you formed a pi bond, 2 pi bonds. So one thing you'll want to have in your mind, an association that you'll want to have in your mind, is that anytime you see halogens, you can do substitution or elimination. Anytime you do elimination, you create pi bonds. If you have only one halogen, then you can only create one pi bond. But if you have two halogens, you can create 2 pi bonds and get an alkyne. And so, really, this is just elimination like we've done before. Just make sure you use this excess strong base followed by water.